Welcome to episode 2. Here I have a standard oldish computer. It has an interesting feature. A power meter built into the power supply. Let's find out how it works. I have not yet tried to turn this computer on. I was given it a few months back. Let's power it up first to see what it does. I did have a sneaky look at the rating on this power supply. It's only good for 220, 230 volt input. I've got an independent power meter here so we can see if it correlates to the built-in power meter. And a good old monitor here plugged into the DVI. Let's power it up and see what happens. Nothing happens so far. Let's try the power switch on the top of the computer. Nothing. Seems to be dead. That's a bit disappointing. Oh well, I guess we won't get to see it running just yet. We can check the standby 5 volts. Okay, I haven't actually done anything yet, but I pulled this out to check the standby voltage, which is there, but now this is lit up just all of a sudden without me doing anything. So let's try again, connect this back up, and we'll try powering it up. Put the monitor back into view. And let's try switching it on again. Push delete. Okay, the power meter doesn't really agree with the external one. 82 watts versus 56 watts. That's a bit off. Okay, the power meter's still a bit out, showing 94 watts now, but we're measuring 130 independently. The load is a bit variable. This meter is always showing more. Okay, let's take apart the power supply and see how that power meter works. Before we open it up, let's think about how the power meter could be implemented. Power is voltage applied multiplied by current flowing. You must measure both or be able to accurately predict one and measure the other in order to calculate the power. Could use an integrated chip that takes care of all the voltage, current measurement and calculations. A shunt could be used to measure the current. It's possible they have used a power factor corrected boost converter on the input, and that way it can produce a consistent DC bus voltage, which they can then assume is always correct and only have to measure the current. It would make this calculation a bit simpler. But you'd think if they had used an active power factor correction, then there wouldn't be a limitation on the input voltage and it wouldn't be only 230 volts. Cut. A huge cable. Yeah, we've released it. What is active power factor? Let's take it apart. Rubber gasket thing That's got fan vibration. Be a tight fit. Looking over this side. Oh, the fan seems to be stuck under the edge of the metalwork. On that side too. And something. More cable ties to cut through. That's the fan feedback wire. We can unplug the fan. Get this as well. Okay. Meters there. 3 wires going to it. Come over here. The red one is a power supply. Goes onto one of the output connectors. Like that might be the, well, it must be the standby 5 volts because the only one that's on all the time that was lit up. Computer was off. Must be a ground and a sense. This connector here. The other 2 wires. Let's take it apart a bit further. Input filtering in the way a bit of the screw there. And the output board in the way of that screw. I think we can off the whole output board with screws here. Thick wires, well, a lot of wires going to it. There's more screws hidden under this label here. That's E. There is another separate board below the input the board or the output connector board, but oh, that's attached to the. There's only 2 screws. That's free now. Main board is free too. Input power connectors wires are soldered onto the main board. Might have to cut through those to get this out. Yeah, put the main board out. Trace the circuits. Okay, so the AC input, live and neutral, some common mode chokes, RFI filtering, NTC or inrush limiting used there, and some heat shrink to stop it exploding or to stop it making a mess when it explodes. And more common mode filtering, the bridge rectifier, this is important, there's possibly a low value resistor there, maybe that's involved with measuring current. 2 microfarad capacitor, let's just filter across the rectified DC. Then we got the inductor for the power factor boost converter. Then on the heatsink behind it, there's a FET there for the boost converter. Gate resistors there, the gate driver. Then next to it on the heatsink is the diode boost converter. Oh, because two of the 3 pins are joined together. Cathodes. Out of the diode, the DC to the capacitor, here 400 volt capacitor. Running quite close to its voltage. Maybe we should have checked that that wasn't charged up before we started. Seems to be good. Another diode there. I think that might be a clamp. Flyback clamp on the FET maybe. Not. Do of reverse currents, reverse voltage spikes, not in the direct current flow. Unplug the meter as we cut off these wires. To deal with that anymore. The output board's double-sided. It's got a lot of parts where there's no solder mask on it, so that additional solder has been laid along it, and also wires have been laid on it in some parts to increase the current capability. Probably got quite thick copper as well. The extra current. In addition to that, there's some copper, single strand thick copper wires there. Look like they're bringing the ground, up the ground. continuing exploring this thing. There, that will be the transformer for the standby 5-volt switcher. Runs all the time. There's another little tiny transformer in there, which will be probably the gate drive isolation pulse transformer. The current meter, these wires here, the red wire there goes all the way over to the standby 5 volts, parallel with the little purple wire which goes to the main board, computer's main board that we always powered. And these other two wires, black and white, capacitor there, electrolytic capacitor, can't read the value of it, and then two thin tracks go down what looks like sort of rectifier. I see what's going on there. This interesting thing here. That will be a buy it. Buy Droid Cam OBS. Get rid of that watermark. Quite cheap. Now, so this thing here is a little toroidal core in there with heat shrink over it. Looks like there might be one burn through the hole in the core. So it's a little current transformer. That's coming from the primary either switching path or DC path. It looks like it's in series with the primary winding on the main transformer. Yes, so we were looking over here, the power factor corrector stuff's on this side of the heatsink. On this side of the heatsink is the bits or transistors for the standby power, the main switching transistors for the main transformer. Two of them there. The winding going to this little current transformer is in series with the main winding of the power transformer. So that single turn through the toroid has multiple turns on its secondary that will be inducing a current flow in the secondary, which then gets rectified by these diodes here, by that little electrolytic capacitor there. It's probably a farad or so. It gets fed to the meter. So that means that they are assuming voltage and then just measure current. Power meter board version 7.1, around 5 volts and in. That chip there, probably a microcontroller, that's sampling that input and the maths, playing a number on the screen. try applying a voltage to that input. See how that relates to what's displayed on the screen. Can't get the label off easily to see what the chip is. Was off. Still can't read it. We'll have to further investigate that. So we've got most of the idea of what's going on. Little current transformer that will be seeing spikes of current. I will take a closer look. The display uses a Holtec, presumably microcontroller. So we'll look that up shortly. For now, let's take out the heatsink along with all of the bits that are soldered onto it so we can work out how it works. It had 3 terminals, but we ripped one of them off. I think that's why it was so hard to get out, because they weren't all in a line like they are for the other devices. Got some 25N50, 21N60, QP4N90, 25N50, common cathode diode. The little 3-pin one will be the switch for the standby power supply. Yes, it definitely is the switch for that. So it has an extra terminal there, which we should have been desoldering. Now that we've taken the parts off the board, we can have a look at the tracks and draw out the circuit. I had to take a few more off that to see what the tracks are doing underneath them. This circuit board seems to be quite poor quality or very low temperature rated, because it was very easy for the pads to rip off with just normal heat application. It doesn't seem normal. The control chip they've used there is a combination PWM controller and power factor corrector, CM6800. Pretty common to use this type of integrated power factor corrector and PWM controller on power supplies like this. See there the internal diagram of the chip, the power factor correction part and the PWM controller part. This is the circuit that I've drawn from inspecting the PCB, looking at where the tracks go. It's fairly similar to what was expected when we were first looking at the board. Input protection, current, inrush current limiting, RFI filtering, bridge rectifier, the 2 microfarad film capacitor, or yellow thing. That is the input capacitance for the power factor correcting boost converter, which is this part. How that works is these bits in parallel get switched on. It causes current to flow through the inductor, through the FETs, through this current sensing resistor, back out. As the current builds up to a predetermined level, when it reaches that, as sensed by this resistor, the FETs will be switched off. As a property of inductors, they want to continue the current flowing. and they'll produce whatever voltage is required to cause that to happen. The FETs are now off. The only way the current can flow is through these diodes and into the main DC bus capacitor, where the boost comes from, because the inductor will produce whatever voltage it needs to cause that current to flow. And there'll be voltage sensing off of that, so that it ends up regulating at a voltage that's higher than the peak mains input. There's two FETs in parallel to handle the peak currents required. They have this gate resistor circuit here. There's a diode across this resistor, which means that when the controller turns the gates off, they will discharge faster by bypassing that resistor. The PWM signal applied to the FETs is adjusted according to the AC sine wave, so that the current drawn follows the sine wave. For the main switching part of this power supply that drives the transformer, it uses a 2-switch Ford converter topology. These two FETs here, they're switched on and off at the same time. The lower one, which is reference to the minus DC bus, is driven directly, and then through a pulse transformer, the high side is driven. When the PWM line is high, both FETs are switched on. Current flows out of the main capacitor, through the top FET, through the transformer, through the power meter CT, which we're going to take a look at, through the bottom FET, through a current sensing resistor back to the capacitor. Again, that current will be sensed, and when it reaches a predetermined level, the FETs will be turned off. At that point, again, because this is an inductor, it wants to continue current flowing, and in this case, the current will flow through these diodes back up to the capacitor and through the bottom side. This topology with two switches allows greater efficiency because you don't need to use a clamp or separate reset winding on the transformer that dissipates that stored energy as heat. Instead, that energy circulates back and goes back into the capacitor. The other advantage over the single switch is that the maximum voltage these will see, these FETs, is the DC bus voltage. Let's have a look at the output side. So that's under this here, the secondary of the transformer, the rectification. I've drawn that out roughly. So it's a Ford converter, has the currents flowing through the primary, the currents flowing in the secondary, through the diodes, through inductors, into capacitors. There's additional filtering there to move the output. When the current's not flowing, when the FETs are off, it stops flowing through here. These filtering inductors will want to have current continue flowing, so that will come through these diodes. There's a bit like a buck converter on the output there. There's a 3.3 volts created from the 5 volt winding using a mag amp circuit saturable reactor, which is that thing there. There'll be a separate controller for this, but I'm not sure where that is on the board. It might be in somewhere on this. And what that will do is it will drive a current in and through that reactor there, cause it to go in and out of saturation, and that will work like a switch, controlled in a way that the rectifier and output out of the circuit, so that it won't see part of the switching operation. This will block the leading edge of the current that flows through here each switching cycle, and through rectifiers and filters. There are articles that explain how these things work a lot better than I have. The final part of the circuit, thing that we came here to look at, is the power meter. So with this CT, which is the weird looking thing in some heat shrink here, little toroid. So every time some current's flowing through the primary of the transformer, that same current flows through the CT, which then gets transferred by its ratio to this side, where there's a small filter, then there's a rectifier, smoothing capacitor, burden resistor, and that will produce a voltage there, somewhat smoothed, it's a fairly high value capacitor, so you end up with a voltage on that point representing the average current that's flowing through there, and then that's representing the display, which is 5 volts ground, and this input signal. Let's have a look at this display and see how it responds to an input on that point there. Found a connector to go on this, and we'll set the current limit to something sensible so we don't just blow it up. That's 5 volts. Polarity is correct. There you go. 56. Nothing. The input. If we bring the input to ground, quite close to 0, but not quite. Variable resistor going up. So halfway, 370. Seems like it's quite a bit of filtering in this. That's a small microcontroller, and the input signal is going to an analog to digital converter. Yeah, we're at full treble, 588. We need to get a recording of what voltage input causes what to display on the screen. So I've taken some readings and created a graph that shows the voltage applied on the input to what was displayed on the screen. Looks like it tops out around somewhere between 4 and 4.5 volts, goes to 588. The response looks fairly linear, so it is just a voltmeter. Now I want to put this back together and see if we can get it working again, and then we'll take some measurements of it while it's running. Going to give this a quick smoke test now that everything's back together. Got the multimeter there on the DC bus. Let's go. Yeah, that looks promising. The power factor correction is not running at the moment, so the DC voltage is just the rectified mains input. The standby 5 volts has come on. We can tell because the display has lit up. Power supply is now hooked up for some testing. Got a DC bus measurement connected here. Goes to this multimeter, currently about 9 volts. On the output, the 12 volt output of the power supply, there's a shunt for measuring the output current. There's a Kelvin connected voltage sense here. There's a bunch of these 12 volt 50 watt light bulbs as a load, and also a couple of resistors. Most of that's off screen. For the AC input, I've got a fairly thick cable here. That's going to be connected to this source, which is around 230 volts. It has a Kelvin connected voltage sense off the back of this socket, and also a link out to a current measurement. Those input and output voltage and current measurements go to a Yokogawa power meter here on screen. And we can see down the left column the input voltage, current, power, frequency, and in the right hand column is the output voltage, current, power, and then a calculated efficiency. And below that we can see the waveforms, currently showing the input voltage waveform. We'll plug in the power supply. And the current is rescaling. At the moment, you can see the DC bus voltage, 326 volts. The power factor correction is not running. Let's switch on the power supply under heavy load. I've attached a switch here to the connector. Just have to wait for the rescaling. And so we've got a bit over 300 watts load. The input there is 380 watts. So the calculated efficiency is around 82%. The green current waveform very closely follows the yellow input voltage waveform, so the power factor for that is quite good. We should probably turn that off, just because we're going to set fire to things with all those light bulbs running. We'll just make a check of the indicated power, 271 watts. That doesn't really match what we see on the power meter over here, 375, 310. We can see when it's running in standby, the power factor correction is not turned on, so the DC voltage we end up with is just the mains voltage rectified there, 327 volts, and you can see the waveform, input current and voltage waveforms there. The current is out of phase with the voltage, because it's not power factor corrected. Interesting, when we switch on the power supply, the DC bus voltage goes up to 393.5 volts there. That's concerningly close to the voltage rating of the DC bus capacitor. It's only rated at 400 volts, pushing it pretty close to the limit there. Let's have a look how this power supply is performing thermally. It looks like the output rectifier heatsink is the hottest there, nearly 40 degrees on the top, and on the input side it looks like the power factor choke, the inductor down there, is hottest, around 40 degrees. The light bulbs over there will be quite hot too. Just switch that off again and unplug it and take a look down the side there. It seems to be only the power factor choke that's getting warm there. It's not concerningly warm, but we wouldn't want to run this for too long without the fan running. Although maybe it doesn't matter too much, because I noticed there's an insulating piece that blocks half of the fan, so when the fan is mounted, there's no direct airflow over the primary side of the power supply. We'll test one more time with a lower load level and see how the power meter correlates with the actual power consumption. 170 watts on the output, 210 watts on the input. The power meter there is closer to what the output load is, but it's still not particularly accurate. Seems like it's good to within about 100 watts. Wouldn't want to trust it any more than that. It's about 20 watts load. It's close-ish. We bump that up to 50 watts with one light bulb. Fairly similar. 100 watts load, still fairly close. 150 watts, seems like error is creeping in there. 200 watts load, similar amount of error. 260 watt. The power meter seems to get further out the higher the load. The next thing we'll look at is what the signal that gets sent to this power meter looks like. I've got the oscilloscope set up now, you can see there with the red screen. I've got the current probe connected to that on channel 1, set to 1 amp per division. We're going to connect the current probe in series with the primary winding and the CT that measures the power around here. Current clamp wedged in place there. Let's switch on the power supply. Hold the oscilloscope, switch that off. You can see there the peak current is around 3 amps. The voltage that's being applied to the display here is on channel 2, about 1.8 volts. The power draw is about 260 watts on the output, 318 watts on the input. If we look at the switching frequency of the converter, 6 divisions per cycle, so that will be 6 times 2.5 microseconds per division. So that's 15 microseconds per cycle, which is around 66 kilohertz. We've got very light load. At 20 watts load, the peak current starts increasing. More light bulbs. Maximum load I can provide, 300 watts on the output, 370 watts on the input, about 4 amp peak. The voltage applied to the meter, 2 volts. 2 volts was applied to that. Alright, that was a bit of a long and rambling mess. Hopefully not too boring. I have realized it's difficult to describe things clearly in detail without any rehearsals or script. Maybe that will improve in time, and maybe I'll have a better microphone too. I'm not sure what more there is to investigate in this. The original intention was to see how the power meter works, and we've done that. Along the way we found out how the rest of the power supply operates, and we also determined that the power meter is not very accurate. To improve the accuracy, it probably needs a software update to adjust the slope, what it displays versus the input voltage, but it's debatable whether there would be much value in doing that. That's all for now.